Hello and welcome to Energy Transformations. Today we'll be talking about what energy is along with energy transformations. We'll discuss the various forms that energy can take and how it changes from one form to another. We'll also learn about the law of conservation of energy and how it applies in our everyday lives. So with all of this talk of energy, what is it? Energy is very hard to describe, but we generally define it as the ability to do work, create motion, or to cause change in matter. Energy is typically divided into two different forms, potential energy and kinetic energy. Potential energy is energy that is stored in an object due to its position, stresses, or electrical charge. Kinetic energy is energy that an object has because of its motion. Now let's look at an example or two. Potential energy is stored energy. This is energy that is stored because of its position. We would call that gravitational energy. This might be an example of a roller coaster at the very top, or a ball or an object held high in the air. Energy can also be stored by stresses that are on the object. An example here might be a bowstring pulled taut with an arrow in it. It can be any kind of mechanical or elastic energy that can be stored in an object. We also have electrical charge, which we would call electrical potential. Bonds between atoms can also store and create potential energy. We call this chemical energy, and we find it stored in batteries as an example. The bonds within atoms that hold atoms together also store energy, and we call this nuclear energy, and it's what we use to run our nuclear power plants. Kinetic energy is an energy that an object has because of its motion. It's easy to picture a bicycle moving or a ball rolling down a hill, but motion can mean a lot more things than just standard motion. Sound is considered a form of motion because waves of sound are moving through the air. Thermal energy is the heat that an object has, and it has heat because of the molecules moving quickly and vibrating within it. So this is also a form of kinetic energy. Radiant energy is light. That is also a form of kinetic energy. Lastly, electrical energy is caused by electrons moving, and so it also is kinetic energy. So how do we use energy? We transform it into forms that are useful to us. Some of the most familiar might be electricity, food, heat, or light. Electricity is a form of kinetic energy. Food contains chemical energy that our bodies can process and use to cause motion in our cells. Heat we use for our homes, and light we use for many things as well. A law that's so important to remember is called the law of conservation of energy. Energy cannot be created or destroyed. It can be changed from one form to another, but it always exists in the same amount. So where does this energy come from? Energy on Earth comes from the sun and from nuclear energy. So let's pause for a moment and think about how do the energy forms that we've discussed in class ultimately come from the sun, with the exception of nuclear energy and geothermal energy, which is partly nuclear energy. Let's think for a moment. The most obvious is solar energy. Solar energy harnesses energy directly from the sun. What about fossil fuels? How do fossil fuels get their energy from the sun? Hopefully you are thinking about the plants that fossil fuels are formed from. Those plants stored energy from the sun in the form of chemical energy that was eventually transformed into fossil fuels. What about wind energy? How does it come from the sun? I hope you were thinking about wind currents. Wind currents are driven by uneven heating of the earth, and the earth is heated by the sun. Hydroelectric. How does hydroelectric power come from the sun? Well, ocean currents are driven by the sun, and we need the sun to drive the hydrologic cycle, which is how rain falls and fills rivers and creates water to flow through dams. Biofuels? Of course, plants use energy from the sun that we then use for biofuels. The sun also provides the energy that drives Earth's weather by unevenly heating the land and water, and by heating the equator and poles by different amounts. We'll dive a lot more into this throughout our unit, but it's important to remember this basic idea that climate and weather are just caused by energy moving around. In our next class, we'll discuss why energy moves around when it is unevenly distributed. Now we're going to watch a short video to show how important these forces are.
What safeguards our solar system is our star. The sun provides a shield, stretching beyond the last planet in its orbit, a force field that deflects these cosmic rays. But these solar winds can be dangerous too, especially during outbursts called coronal mass ejections. Want a vision of Earth gone wrong? Just look at what solar storms do to our sister planet, Venus. They strip away lighter elements in its upper atmosphere. Hydrogen, oxygen, and the molecule they form, water. What's left is a witch's brew of noxious chemicals, including thick sulfurous clouds. How has Earth avoided the grim fate of Venus? We can see the answer as the solar storm approaches Earth. Our planet has a protective shield all its own, a powerful magnetic field generated deep within its core. In fact, that's just our first line of defense. Much of the solar energy that gets through is reflected back to space by clouds, ice, and snow. The energy that Earth absorbs is just enough to power a remarkable planetary engine, the climate. It's set in motion by the unevenness of solar heating, due in part to the cycles of day and night and the seasons, that causes warm tropical winds to blow toward the poles and cold polar air toward the equator. Wind currents drive surface ocean currents. This computer simulation shows the Gulf Stream winding its way along the coast of North America. This great ocean river carries enough heat energy to power the industrial world 100 times over. It breaks down in massive whirlpools that spread warm tropical waters over northern seas. Below the surface, they mix with cold, deep currents that swirl around undersea ledges and mountains. Earth's climate engine has countless moving parts, tides and terrain, crosswinds and currents, all working to equalize temperatures around the globe.
So, we've looked at how all energy comes from the sun. Let's look at a specific example. You have to break energy transfer down into many steps. But let's think about, how does energy get from the sun to my car? It starts out with plants collecting energy from the sun in the form of light and converting it into chemical energy stored in their leaves and stalks. Then this chemical energy is still stored in the plants when they die. As they break down and form oil, that chemical energy is still there. When we refine that oil into gasoline, that chemical energy is still there. And when we put it into our cars and burn it in the internal combustion engine, it transforms into motion in the engine, which transforms into motion in my car. This is certainly a simplification, but pretty much all energy that we use, with the exception of nuclear, we can trace back to the sun with enough steps. However, the sun puts out way more energy than it took to run my car, and those plants stored a lot more energy than it took to run my car also. So we want to measure energy so we can understand how much we use and what happens to the rest of it. Energy can be difficult to quantify, particularly potential energy. We are only going to look at one equation in this unit, and this is for gravitational potential energy. This is the amount of energy that an object has by its distance above the surface. So the gravitational potential energy is equal to the mass of the object times 9.8 meters per second squared times its height off the ground. Try to keep that in mind because we're going to come back to this example later. We have many ways to measure kinetic energy, and we're not going to go into a lot of detail, but I wanted you to think about a few of these units. I'm guessing that you've heard them before. Sound is measured in decibels. We might think of that as loudness, but that's actually the amount of energy that it carries. Light is measured in lumens, and we're going to do a lab in class that shows us the lumens of different light bulbs. Electricity is measured in electron volts or kilowatt hours, which is what you see on your electric bill. Thermal energy in the form of heat can be measured as joules, calories, therms, or BTUs. You may have seen on the side of your boiler or furnace how many BTUs it is. This is a measure of the amount of heat that it can produce. Heat is the amount of thermal energy that an object has. It's different than temperature because it takes into account the size of the object. So for example, if I had a bowl of water and a swimming pool of water, they might be the same temperature, but the swimming pool would hold much more heat because of its size. Temperature is hopefully familiar to all of us and is measured in Celsius, Fahrenheit, and Kelvin. And that calorie that we use to measure heat, yeah, that's pretty much the same calorie that we use to measure the energy in our food also. So we talked about how those plants absorbed more energy than it took to drive my car, but we don't lose that energy. We've already talked about the law of conservation of energy, that energy cannot be created or destroyed. It's only converted from one form to another. So if not all of the energy that the plants absorb is converted into energy to run my car, what happens to the rest of it? We often talk about this energy being lost, but it's not lost. Where does it go? It's just transformed into a different form, typically heat. If we look at this runner, he's burning more food than it would take to move his body the number of miles that he's going, but that extra energy is going into heat. This is why he feels hot and he starts to sweat and perspire to try and cool himself down. Not only our bodies do this, our car engines heat up. That's lost energy. We refer to this as efficiency. Efficiency helps us understand how much energy we're using for the useful thing that we want to do with it. It's measured as useful energy output over total energy output. You might think of this like your grades. Your grades are calculated by the amount of points you got over the total points possible. It's very similar for energy, the amount of useful energy over the amount of total energy. And for both your grades and efficiency, we want them to be as close to 100% as possible. Let's think about this roller coaster. When it starts at the top, it has only potential energy because there is a moment when it's not moving. Its energy is stored because of its distance above the ground. But as it moves downhill, that potential energy is changed into kinetic energy. As it moves downhill, that kinetic energy will increase as the potential energy decreases. And then, when it gets to the bottom, the roller coaster will be converting that that kinetic energy back into potential energy. As it starts moving up the hill, it starts going slower and losing kinetic energy. And as it gets higher, it's gaining potential energy as its distance above the ground. But if you've ever ridden on a roller coaster, you know that it doesn't get as high on the second hill. It starts going up, but it can't go all the way back up. If we learn that energy doesn't disappear, where is the missing energy, and why doesn't it get as high as it was the first time? Let's think for just a moment. I hope you were thinking about the heat that the roller coaster caused, the friction against the rails, and the heat of the roller coaster itself underneath the cars of the roller coaster seats. This is where that missing energy went. Let's look at another example of a ski jumper. The ski jumper starts at the top of the hill. What type of energy does he have? You're right, gravitational potential energy. He's standing still, high above the ground and looking down. When he starts to go down the hill, what happens to some of his potential energy? Like the roller coaster, it is changed in kinetic motion energy as he moves down. As he loses more and more potential energy, he gains kinetic energy as he moves faster and faster. He gets to the bottom of the ramp and he takes off. Then what happens? Some of that kinetic motion, just like the roller coaster, is changed back into gravitational potential energy as he rises higher in the air than the bottom of the ramp. Let's take a look at this silly ski jumper. How could he give himself more potential energy? Remember that equation that we looked at? He can either raise his starting height or add more mass. If gravitational energy is mass times the speed of free fall the speed of free acceleration times height, he can either increase his height or his mass to gain potential energy. Let's take a look at a fun video now. Fortunately, that skier wasn't hurt in that fall, remarkably enough. So let's think for a minute. When the skier lands and has stopped moving, does he have any potential energy? Yes, he actually does. He stores potential energy in his own body due to the food that he's eaten and the bonds between his own cells. He's a form of living matter, so he is storing energy. Let's look at a few more examples of energy conversion. What kind of energy conversion takes place when we light a match? I'll give you a hint. It starts as one form and turns into two. Let's think for just a moment. First of all, what kind of energy does the match itself have? It has chemical energy, and that chemical energy is changed into thermal energy and radiant energy, or heat and light. Here's a question: how would we calculate the efficiency in this reaction? This is a tricky one because efficiency is useful energy over total energy. It depends on what we're using the match for. If we're using it only to light a candle, then the energy that converts to light is actually lost. But if we're using it to light our way through a room, then the energy used for heat is not useful energy and might be considered lost as well. Let's look at another example. What kind of energy conversion takes place when we light fireworks? This time it starts with one form and turns into three. What kind of energy do the fireworks have? They also have chemical energy. and it's changed into thermal energy, radiant energy, and sound. One more example. What kind of energy conversion takes place in a light bulb? This time 1 turns into 2. What kind of energy does the light bulb start with? Electrical energy that it receives from when we plug it in. And that's changed into thermal energy or heat and radiant energy or light. We're going to do a lab today where we learn more about this and quantify this energy if you're in class. Now you try. These are the questions that you can answer at the bottom of your worksheet. Let's look at an example of a bungee jumper. Name the type of energy this bungee jumper has at each stage of her fall. What type of energy does she have at the top, in the middle, at the bottom? Number 2, what kind of energy transformation is taking place when you boil water on this type of stove? And number 3, what kind of energy transformation is taking place when trees grow in the forest? I hope you got all these right. We'll be checking them later. Now we're going to watch one more little video. I hope you enjoy.
9 p.m. The streets were meaner than a Rottweiler with a migraine. I had a hunch energy was being lost in this town, and I was investigating where it was going, for I am the energy detective. I'd had a tip-off I should watch out for Debs McGrail. Said she had useful information I might find useful. Suddenly I saw her. Debs McGrail?
I've been expecting you.
I've heard that there's energy being lost, and nobody loses energy in my town.
You've got it all wrong.
Listen, lady, don't play the fool with me. Losing energy is a crime, and besides, it's wasteful.
But you can't lose energy. When you use it, it just gets transferred. Don't you understand?
You're asking if I, the great energy detective, don't understand? Actually, I don't.
Take your car. The energy comes from the petrol in it. What you want is for that energy to be transferred into movement or kinetic energy.
Sure.
But only 30% is transferred into movement.
30%? That means I'm losing, a lot.
But that's the point. It's not lost. It's just transferred.
What to?
Mainly heat. Parts of the car heat up, engine, tyres, and they heat the air and road around them. The exhaust pipe heats up too, and that heats the air. Then there's sound. That's energy being transferred to particles of air, which vibrate and carry the sound to you.
Wow.
But here's the main point. If you add up all that the energy is transferred into, it's the same as the energy that was put in. Nothing is lost.
It was all too much. I felt in need of a science in action graphic. I got it. If the total available energy is 100%, the useful energy is what goes into movement, 30%. The rest is energy that gets transferred into things that ain't so useful. So nothing is lost, just changed. I was beginning to understand. But surely there's a principle at stake.
You can't create or destroy energy. It just gets transferred. It's called the principle of the conservation of energy. It's not lost or destroyed.
See, there was a principle at stake. So, only 30% useful energy from my car. That's not very good, is it?
And as for that torch,
Not my torch.
the energy in the batteries is transferred into useful light and useless heat.
I prayed she wouldn't tell me what the useful energy was.
Useful energy, 5%.
She told me. We said our goodbyes and I went back into the night. Now I knew of all the energy in all the towns in all the world. None of it was ever lost.
All right, thanks for watching. Hope you enjoyed.